So I will be presenting our paper, LiveTag, Sensing Human Object Interaction Through Passive and Chipless Wi-Fi Tags. So different from most papers in NSDI, this is actually a wireless sensing paper, and I hope you will enjoy it. So many types of human activities involve interaction with physical objects, and information about interaction is an essential input to many applications in ubiquitous computing and help them to understand human activity. Well, this could support many activity-aware applications, such as stroke rehabilitation assessment in home environment, consumer analytics in a retail store, and if we can detect how often a person interacts with his water bottle or cup, we might be able to infer his water intake and even hydration level. Alternatively, we can turn a passive object into a touch and command interface, like a control panel. So interaction usually needs an interface, and partially due to the surge of mobile devices, touch has been one of the most dominant and familiar way of interaction to most people. So we ask ourselves this question: can we detect touch interactions on everyday objects? Well, you might think about your smartphone. We have touch screen for that job. However, equipping a touch sensor or touch screen to every object around us is apparently impractical. And to realize such a vision, we made the following 4 design goals. Our system needs to be able to detect touches on passive and non-smart objects, such as a wall, a sofa, a chair, or even your clothes. To make it scalable and practical, it needs to be low cost and requires minimum additional hardware. Finally, it should be battery free. Otherwise, the maintenance cost would be too high. So following these design goals, our solution, LiveTag, is essentially a chipless and passive Wi-Fi tag that has touch detection capability. Each tag is only as thin as a piece of photo paper and can be attached to any objects to serve as a touch interface. And as you can see from the photo, the tag is even flexible. You can bend it and it still functions. Now these tags have copper film atop the substrate, and the copper film have specially designed geometry shape such that they form multiple touch points as marked in the figure. And they can be detected by our commodity Wi-Fi devices, like our Wi-Fi access point or even your smartphone. Imagine with LiveTag, we have the ability to turn passive objects around us interactable through touch. In fact, not just touch, any types of physical contact can be detected as well. These tags can be deployed, for example, in a smart home environment to detect all kinds of human activities and interactions. For example, the tag can be on the armrest of your sofa to detect how many times you sit down on it. It can also be on the handle of a fridge to see how often you use it. It can also be attached to a wall to serve as a control panel for all the smart appliances in your home. And finally, all the interactions will be detected by the Wi-Fi devices, such as the Wi-Fi access point in your home that is already in your home environment. So before going into a lot of technical details, I'll first provide an overview of how we realize such a system. The system contains 3 physical components: the tag, a Wi-Fi transmitter, which can be the access point, and the Wi-Fi receiver, which can be the smartphone that user carries. Well, the tag will actually reflect and modulates the incoming Wi-Fi signal's frequency spectrum, which can be detected by the Wi-Fi receiver. We designed the shape of the metal conductive layer of the tag such that they create unique amplitude frequency responses in Wi-Fi frequency band, and we use that as the signature of the tags. Finally, when the tag is touched, the frequency response actually changes, and that's how the receiver can detect the touch event. To deal with multipath fading and line-of-sight interference, we designed special beamforming mechanisms enabled by Wi-Fi access point's multiple antennas. Next, we will present the complete design of the system. First, I'll show how to design a tag such that they can be detected by Wi-Fi. Then I will introduce the signal processing algorithms that enables robust detection. We use the unique amplitude frequency response patterns of the tag as the signature. And in general, the transmitted Wi-Fi signal has a trapezoid shape power spectral density as specified by the Wi-Fi standard IEEE 8211. The signal is picked up by the tag's antenna, which is dual-band, and then passes through a signal transmission line. The transmission line has a series of resonators sitting beside it. These resonators are essentially band-stop filters. Each of them would modulate the incoming Wi-Fi signal and create a notch in the frequency spectrum. At the end, the signal passes through the transmission line will be received by the Wi-Fi receiver, who can look for these notches in the frequency spectrum by extracting something called channel state information, and this is supported by a wide range of commercial Wi-Fi chips already. The designs of the resonators are actually well studied, and we simply choose a few standard structures, such as the spiral pattern shown in this figure. When the resonator is touched by a finger or anything conductive, actually, it is detuned, and the notch actually shifts away in the frequency domain. So in the eyes of the Wi-Fi receiver, the notch simply disappears. So it can be, so that's how it can detect the touch. To enable multiple touch points on a single tag, we use multiple resonators with different notch frequencies in the spectrum. The Wi-Fi receiver can actually monitor which notches are shifted away, and thus can distinguish which resonators are touched. So imagine now you have a tag with multiple buttons, and your receiver is able to detect which buttons are touched. This photo shows a tag with 9 touch points, enabled by 36 resonators. Each blue square marks a touch point, and the touch point is actually made of 4 identical resonators of the same notch frequency. We use 4 identical resonators to enhance the depth of the notch for better detection performances. Simple as the working principle may sound, we actually went through an exhaustive process to optimize the tag structure for the best performance. The frequency response of the tag is actually determined by all these geometry shape parameters that we mark here. Through a series of evaluations, we identified some very interesting insights, and here are a few examples. We find that adjusting the resonator dimension is the most effective way to control the notch center frequency. By placing the resonator closer to the signal transmission line helps create deep and very narrow notches, which we absolutely desire. Finally, to enable multiple touch points on a single tag, we find that there has to be a minimum separation between adjacent resonators so that the notches they create are independent, unaffected by each other. Finally, we were able to place up to 9 notches in the entire 2.4 and 5 GHz band of Wi-Fi spectrum. Hence, we can place at most 9 touch points on a single tag. So up till now, things look perfect. We have a chipless and passive Wi-Fi tag that can be detected by your commodity devices. Is this everything we need? Unfortunately, in practice, the detection faces several significant challenges: multipath fading and line-of-sight interference. Before explaining how we deal with these 2 challenges, we explain how the device actually obtains the tag signature. To aggregate as much bandwidth as possible so that we can stack more notches in the frequency domain, we have the Wi-Fi transmitter to send packets on every Wi-Fi channel across 2.4 and 5 GHz band. The receiver hops the channel together with the transmitter. And the receiver actually extracts the channel state information on each of the channel. Finally, it stitches all the information together to obtain a complete frequency response profile of the tag for further identification. Well, in practice, Wi-Fi signal experiences severe multipath effect. Let me explain what that is. In addition to the direct transmission paths, the signal also actually travels through a number of reflection passes to reach the receiver. Because these passes have different path lengths, the signal may be constructively or destructively combined at the receiver, depending on the frequency. And multipath fading actually also creates very deep notches in the frequency spectrum, similar to the tag. So there's a confusion here. If we look at a notch in the frequency spectrum, now this figure actually shows 2 notches, how do we know if the notch is created by our tag or simply caused by multipath fading? To solve this problem, we leverage the fact that fading notches depend on the signal passes that the signal travels through. So in other words, if the signal actually hits a different set of reflectors, then the fading notches may change. So here's our solution. By performing something called beamforming, we create directional signal beams, and we steer the beams to different directions during the transmission, so that the signal in this beam is likely to hit different reflectors in this process. And during this beam steering process, the fading notch is likely to change constantly, but the tag notch will persist. So in this very simple example, we show that notch F2 is persistent. And as a result, we know that this notch is created by the tag, while the others are simply caused by multipath fading. In practice, we find that using 4 antennas on the Wi-Fi transmitter is already sufficient, and a large number of commercial 802.11ac Wi-Fi access points also supports 4 antennas on them. Another very important issue is self-interference. So in the receiver's received signal, the tag's reflected signal is actually much weaker compared to the signal on the direct path between the transmitter and the receiver. This makes the tag notches very difficult to detect. So to suppress this kind of self-interference, we also use beamforming. We first have the Wi-Fi receiver to transmit a packet to the access point, and then the access point uses multiple antennas to perform receiving beamforming to figure out the line of sight path direction. Then, during the transmission, the transmitter always creates a null towards this line of sight direction. Of course, this kind of nulling is far from perfect. It is actually a trade-off we make by using commodity Wi-Fi devices that don't have full duplex capability, like dedicated expensive hardwares, for example, a full duplex radio or an RFID reader. For touch detection, the Wi-Fi receiver monitors the change at each notch position. So we find the notch amplitude actually follows a Rayleigh distribution, and thus we formulated a constant false alarm rate detection algorithm with an adaptive detection threshold. So at runtime, the detection threshold changes automatically to maintain a fixed false alarm rate as specified by the user or the programmer. To further improve detection robustness, we provide the option to use multiple redundant resonators with different notch frequencies to serve as a single touch point. So when a finger touches these multiple resonators, a number of frequency notches with different center frequencies will disappear at the same time. This maintains detection accuracy even when some of the frequencies are affected by multipath fading. And so much for the design part. We primarily evaluated our system with software-defined radios, simply because it's easier to perform beamforming on them. But we do demonstrate the feasibility with Linux PCs equipped with standard Qualcomm Atheros Wi-Fi chips. And here are some key evaluation results. With 4 antennas on the Wi-Fi transmitter and a single antenna receiver, both the tag and touch detection accuracy are over 95%. But the current detection range is still limited. The distance between the transmitter to the tag can be around 4 to 5 meters, which is already sufficient to enable room-level coverage. but the distance between the tag to receiver is still short, only around half a meter actually. However, we think this is not a severe problem because the receiver can be the smartphone that user carries in his pocket, which is generally close enough to the finger touch position. And finally, we present a few real-world use cases enabled by LiveTag. This is a tag with 9 touch points with 36 resonators. It can serve as a touch command interface, such as a control panel in your smart home, to control the lighting, the air conditioning, the garage door, and so on. And with our robust detection algorithms, almost all 9 touch points have over 95% of accuracy for touch detection. And this is an interesting application. Apart from detecting touches, we also prototype a tag that can detect water level in a bottle. We imagine that this can be used to monitor water intake. The tag has a series of vertically arranged resonators with the same notch frequency. We place the tag on the water bottle, and similar to a finger touch, water also detunes the resonator, although the water and the resonators are separated by the plastic. So as you can imagine, as the water level in the bottle rises, more resonators falls below the water line and are thus detuned. So the overall filter gain of the entire tag increases as the water level goes up. And the Wi-Fi receiver is able to detect all of this. And to summarize, LiveTag has the potential to bring touch sensing to any passive objects with our passive chipless Wi-Fi tag and the commodity Wi-Fi devices. Some of our future works include tag manufacture with conductive inkjet printing technology to further cut down the cost and to support the flexibility for customization. We would also like to consider new detection algorithms to extend the detection range. And thank you. That's all for the presentation. Thank you for listening.
Thank you. Any questions?
Hi, it's a great talk. So I was wondering, the distance from the transmitter has to be 4 to 5 meters. If that decreases, do you increase the distance from the receiver? Like, is there a trade-off that if I put the transmitter 1 meter away, then the receiver can be like 2 meters away? Or is it independent of that?
Okay, thank you for the question, Hethan. So in our evaluation, we do find this kind of patterns. However, it's not so symmetric. We find that even if we place the transmitter like super close to the tag, the distance between the tag and RX is still pretty short, no more than 1 meter. We think the asymmetry comes from the fact that we use multiple antennas to perform beamforming on the transmitter. But for our system to be practical, we always assume that the receiver can only be a single antenna device.
This is Sherry Young from Intel. My question is regarding similarly towards the distance from the tag to the receiver. So what's the fundamental reason that the range is limited to 0.5 meters? Is it because of the signal strength, or is it because of the detection accuracy, or what's the kind of fundamental constraint out there?
Thank you for the question. So we actually went through a long process, also try to identify this problem to figure out what's going on. So we think it's not due to signal strength. You can simply increase the power to extend the range. However, we find that this doesn't work. We think the primary problem is still that we didn't deal with the multipath fading and line of sight interference perfectly. So consider with an RFID reader and an RFID tag, each RFID reader is essentially a full duplex radio. It can cancel the self-interference almost perfectly. And that's how you can receive the very weak signal reflected from the tag. However, in our case, because the nulling and the multipath fading suppression is far from perfect, we find that the signature of the tag is still pretty weak once the tag is further away from the receiver. And we think that's the fundamental reason of the low detection range.
Thank you. One more clarification question. Why do you need to hop over all the channels?
Yes. So typically, each Wi-Fi channel period to 802.11ac it's only around 20 or 40 megahertz. So as I mentioned, each resonator is essentially a bandstop filter. Of course, we hope to create narrow notches, right, so that multiple notches can be placed within these Wi-Fi channels. However, even though we optimize the text structure, the notch frequency, the notch in the frequency domain is still pretty wide. So to enable multiple touch points, we need to place multiple notches in the frequency spectrum, and that simply cannot be done in a single Wi-Fi channel. We aggregate more channel to collect more bandwidth so that we can place more notches in the frequency domain.
What's the notch frequency range?
So in 2.4 gigahertz band, basically each notch is around 60 to 80 megahertz wide. So that's why we have to use multiple channels.
How about 5 gigahertz band?
In 5, it's basically doubled. So with the same structure, the quality factor of each filter is fixed. Quality factor is the ratio between the notch depths and the notch width. So as you double the frequency, the notch width also doubles.
Thank you. Very good.
Thank you
We
for the
have time
question.
for one more question.
Hi, this is I really love this talk. So you try to make this chipless so that it's very deployable, and you get a single piece of metal that does the job for you.
Mm-hmm.
If you had the flexibility of putting in a chip, could you perhaps extend the range or improve the signal strength by having an on-off pattern that could amplify whatever signal you're getting?
Exactly, you're absolutely right. So, as you probably know, there's something called backscatter communication, and they also have a work this morning. So the basic idea is that they build a circuit with some chips and components such that they can reflect ambient Wi-Fi signals. And actually, there has been such a work that they use backscatter to make a batteryless touch sensor, which essentially achieves the same kind of functionality. And they actually have longer detection range than us. So our primary difference is that each tag is totally passive and doesn't contain any independent circuit components. We imagine that by doing this, our tag can be manufactured by conductive inkjet printing technology, which could really cut down the cost and even allow customization. The intuition is that you can even do this at home with conductive ink and the normal inkjet printer. And that's more like a design choice we make over backscatter.
Thank you.
Okay.
I actually have a question.
Yeah.
About mobility.
Mm-hmm.
So let's consider a scenario you have a user with smartphone as a
Mm-hmm.
receiver in the
Mm-hmm.
pocket, and with hand holding a bottle, you'd like to sense the interaction with the bottle, right? There are two mobility.
Mm-hmm.
Number one is a human can walk around. Therefore, your loud point to the transmitter have to be still as I move. And then my hand could move around, right? So that means the beamforming to focus on the bottle also need a track, right? Have
Yeah.
you studied this type of mobility? How will your system work on
Yes, we did. So as you mentioned, if the user actually moves, that means the Wi-Fi receiver also moves with him. So
Right.
in this case, we find that it will degrade the detection performance because sometimes if the update of the nulling direction doesn't really follow up, then there's a problem. However, for the other kind of mobility, for example, just the normal environmental dynamics, like people walking around beside the tag, we find that they don't have any negative effects on the detection. So because we actually steer the beam to create diverse multipath fading profile.
So basically, your beam can scan much faster than people move around in the room.
Exactly.
Okay.
Yeah.
All right.
Yeah.
Okay. Thank you. Thank our speaker.
Thank you again.